Okay, let's talk a little bit about sequences. I've listed here a few sequences. A sequence is simply a list of numbers. So here's a sequence, right? 1, 3, negative 4, pi, 6, 100, square root 2, 6.84198, comma, and the list just goes on and on and on. Here's another sequence here. Let's get that. This here, 3, 3.1, 3.14, 3.141, 3.1415. Do you see a pattern in this one? The first one had no pattern. This one has a pattern. Can you guess the next one? Yeah, if you guessed 3.14159, you're right? And then it goes on from there. You know what it is? Yeah, it's the digits of pi. I keep adding an extra digit to pi. And now we have, this one is another sequence here, right? 2/3, negative 3/4, 4/5, negative 5/6, 6/7, and it goes on. And this one also has a pattern. Can you guess what the next one for this one is? Give you a moment. Well, it looks like it's alternating positive, negative, so the next one's going to be negative. And the numerator is increasing by 1, and the denominator is increasing by 1, so it's going to be 7/8. Right, and the next one after that would be positive 8/9, and so on, assuming it continues with that pattern. We don't know for certain if it does, right? It's just some sequence, could be arbitrary, but assuming it continues. And here's another sequence: 1, 1, 2, 3, 5, 8, 13. Now, some of you may recognize this sequence. This one is, yeah, it's what we call the Fibonacci sequence. And we get it by adding the previous two elements. We start with 1, 1, and we add those, and we get 2. Then that's this one here. Then we add those, and we get 3. And of course, that's the next one. We add those, and we get 5. That's the next one. And so on down the road. So if that's, in fact, the sequence I'm looking at, of course, I only see a finite number of terms, but I'm guessing that's the sequence we're looking at. 8 and 13 would be 21, right? 8 and 13 is 21, and 13 and 21 would be 34. 21 and 34 would be 55, and so on down the road. Okay, now in calculus, a lot of the sequences we're going to be dealing with are ones that are like this pink one here. This one is defined by a formula, actually. If I asked you what the 500th term of the sequence was, could you tell me? You might be able to guess. Well, if we call this the first term here, and this other one the second term, and this one the third term, we can describe this sequence by A1 equaling, let me make that a darker pen. So A1 equaling 2/3, A2 equaling negative 3/4, and so on. So the question is, what would AN be in that case? So we're looking at this sequence here. What would AN be? Well, A1 is 2/3, so it looks like the top, and A2 is 3/4. It looks like the top is going to be the number that we have here, the subscript plus 1, right? And the bottom is going to be what? The subscript plus 2. So I'm going to get n plus 1 times n plus 2. But how do I get it so it alternates? How am I going to tell whether it's positive or negative? Well, you can kind of see the even ones are negative, right? So I could just say, well, if I look at the 500th term, it's going to be 501 over 502. And since 500 is negative, is even, that's going to be a negative term. But a nice way to describe that is think of -1 raised to a power. So I wanted to start with a positive one. If -1 is raised to an even power, so it's going to be positive. And if I'm starting with 1, if I start with the term 1, then the first term here is going to be, the first power on AN is going to be n plus 1, and which is 1 plus 1, which is 2. That's even. That's going to be positive. negative 1 to the 2 is going to be positive, and then when I have n equals 2, this is going to be 2 plus 1, which is 3, which is odd, and you'll find that you'll alternate between even and odd, and therefore you're going to alternate between positive and negative. Okay, let's do some practice on these. Okay, so I'm introducing a little bit of new notation here. I've got 3 sequences that are defined by a formula that gives me the general nth term. Now what this notation means is that I'm going to list the numbers inside those curly brackets. Some books you'll say square pointy brackets instead of curly brackets, but in our text we use curly brackets, so I'm going to stick with that. Although I kind of want to emphasize the order you list things in matters with sequences. So when you see something that has a formula in n in curly brackets and it says n equals 1 to infinity, what that means is you're looking at the sequence that I get by plugging n equals 1, then n equals 2, then n equals 3, and I go through all the natural numbers from 1 on into that formula. So this would be the sequence. When I plug in 1, I get 2 over 3, right? When I plug in 2, the next number, this is n equals 1 here. When I plug in 2, the next number, I get 4 over 5. When I plug in 3, the next number, I get 6 over 7, right? And so on down the road. So this would be n equals 2. And this would be n equals 3, right? And so on. And you could keep listing. And if I asked you what the 100th term of the sequence was, well, you would just plug in 100, and you'd say, oh, it'd be 200 over 200 plus 1, right? Okay. Now this one, let's do this. Notice in this one I start with 0 rather than 1. You really can start at any integer that you want. As long as everything that formula is defined for that particular integer. So if I plug in n equals 0 here, I'm going to get 6. Well, negative 1 to the 0 is going to be what? That's going to be 1, exactly. So that first term, the 0th term, is going to be 6 plus 2, which of course is what? 8, right? The first term then is going to be what? Well, when I plug in 1, I get negative 1 to the 1, which is negative. I get 6 minus 2, which of course is 4. And now so this is n equals 0 here, right? This is n equals 1 here. And when I do n equals 2, I get what? Well, negative 1 squared is 1. That's positive. I'm going to get 6 plus 2 again. I'm going to get 8 again. If I plug in n equals 3, negative 1 cubed is negative 6 minus 2. That's going to be 4 again. And you can see this sequence just repeats. 8, 4, 8, 4, 8, 4, and so on. Now, notice I started with n equals 0. Sometimes that's convenient, but sometimes we might want to change that. We can always describe this in terms of n equals 1 to infinity as well. Well, notice that in this case, the only thing that changes with n is the exponent on the 1. If I start at n equals 1 to infinity, I want to make sure that I start with an even exponent, right? So I could do negative 1 to the n minus 1. 6 plus negative 1 to the n minus 1 times 2. Now notice, if I plug in 1, that n minus 1 is 0. If I plug in 2, that n minus 1 is 1, and so on. So I'm getting exactly the same thing as starting with 0 over on the left-hand side here. Okay, in fact, let's go back to this one. We could start this one at 0 too, but it would change the formula. So what would I want to do here if I started n equals 0 to infinity? Well, when I plug in 0, I want it to be like I'm plugging in 1 in this thing, right? So if I say 2 times n plus 1, right? 0 plus 1 is 1, 1 plus 1 is 2, so on down the line, and 2 n plus 1 plus 1. Because now when I plug in 0, it's like I'm plugging 1 into the blue over here. When I plug in 1, it's like plugging in 2 into the blue, and so forth. In fact, you can start at any integer, right? Let's say if I wanted to start at at n equals, let's say, 4 to infinity and get exactly the same sequence, right? If I wanted to start at 4, well, when I plug in 4, I would want it to be like plugging 1 into the blue side, right? So how do I get to 1 from 4? It's going to be n minus 3, right? So now when I plug in 4, I get 1. When I plug in 5, I get 2, and so on down the line. You can always switch your starting index, but your formula changes accordingly. Okay, now this one, let's look at this. First, I did this partly to introduce to those of you who are new what factorial means. And factorial is, well, n factorial is simply n times n minus 1 times n minus 2, dot, 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 all the way down to 1, right? And, well, that makes sense, except for notice I'm starting at 0 here. I'm not starting at 1. So what is 0 factorial? Well, it turns out we just define 0 factorial to be 1. I know that sounds odd, but every formula that factorial comes up in, 0 factorial, it just makes sense to call 0 factorial 1. So that's what we're going to do. Okay, so this would be, this thing here would be, at n equals 0, I get 0 plus 1 over 1, I get 1. At n equals 1, I would get 1 plus 1 over 1 factorial. What is 1 factorial? That's just 1, right? So 2 over 1, I'd get a 2. At n equals 2, well, I'd get 2 plus 1, 3 over 2 factorial. And what's 2 factorial? Well, that's 1 times 2, right? Which is 2. Okay, next one's going to be n plus 1, which is 4, 3 plus 1, which is 4, right? So this is the 0th term, first term, second term, so we're in the third term. So 3 plus 1 is 4 over 3 factorial. Well, notice that 3 factorial is simply 2 factorial, right? 1 times 2 times 3. So it's 2 times 3, which is 6. And when I plug in n equals, where am I to? 4, I get 5 over 4 factorial. And 4 factorial is going to be 3 factorial. So 4 factorial is going to equal 3 factorial times 4, right? Because that's going to be 1 times 2 times 3 times 4. And that's, of course, equal to 6 times 4, which is 24. Okay, and so on down the road. Okay, so let's see if we can go backwards from here now.